Welcome. So this is all a bit rushed, so I apologize if there are any rough edges around this. We basically decided on Friday night that we will be doing this. But welcome to our virtual lab, bare metal reverse engineering and hardware hacking. We will look a bit at reverse engineering a bare metal firmware, and then Dmitry will take over and talk a bit about doing a hardware attack to bypass a chip security measure. Now, okay, I also just learned that I'm in the wrong Slack channel, but basically I just posted the crack me that we will reverse engineer into Slack. So if you want to join at home, feel free to download it, and also download Ghidra and SVD loader, and then you'll be able to do what I do, basically. And also, if you have any question, please just post them into Slack. I'll try my best to answer as soon as I see them. So let's start by talking about bare metal devices. So we all know about smartphones and so on, which have very powerful processors, but there are a lot of devices around us that have less powerful processors in them, such as hardware wallets or general IoT devices, fitness trackers, and even in cars. If you take a car apart, you probably find 200 different processors that don't run a real operating system. So let's talk a bit about what bare metal means, so we are all on the same page. So on a normal computer or on a smartphone, an application that you write will run on top of an operating system. And this operating system will then use drivers to talk to the actual hardware. Now, on a bare metal device, our application runs directly on the hardware. There's no real operating system. There's no large hardware abstraction and so on. Instead, for each hardware we run on, we have to ship all the drivers and all the stuff that we need to talk to the hardware with our application. Now, the best example in our circles for an embedded device that is not bare metal is probably the Raspberry Pi, because in most cases it runs Linux, even though you can program it bare metal. Only a few people are crazy enough to actually do it. And then on the bare metal side, the most popular example is probably just the Arduino. Now, today we will look at bare metal devices based on ARM processors. And ARM has a lot of different classes of processors. For example, we have the Cortex-A, we have the Cortex-M, we have the Cortex-R, and so on. And the Cortex-A are the big processors that you have, for example, in your smartphone. The Cortex-R are the processors for real-time applications, such as in industrial or automotive controls. And then we have the Cortex-M, which is the microcontrollers. And today we will only look at Cortex-M devices. Now, what makes a Cortex-M device is that it has no memory management unit. So there's no virtual memory. There's no real way to run a real operating system with like process isolation and so on it. And also compared to a Cortex-A, they are very slow. So they start at like 20 megahertz or so and go up to a couple of 100 megahertz. And they have very small amounts of flash and RAM. So for example, in most cases, you have a couple of kilobytes of RAM really. So there's not a lot of space on most of these devices. Also, most of the ones that are on the market right now are single core, even though dual core and even more cores are getting more and more common. Now, it wouldn't be ARM if there weren't 100 different versions of Cortex-Ms. And so, for example, there's Cortex-M0, M0 plus, M1, M3, M4, and so on and so forth. And Wikipedia has this great graphic, this great table that shows you what's what. And basically, we, as hackers, we don't really care about the differences between these processors. But for example, the instruction pipeline is different, and even the computer architecture. And so, for example, all the smaller Cortex-M0s and so on are based on the von Neumann architecture, while the M3, M4, and so on are Harvard-based. But we don't really care. But one more thing to note is that the ARM architecture, so the instruction set you can use on these, is also different. And so, for example, on the M0s, you need to use an ARM v6M assembler, and on the M3, you need an ARM v7. But today, we don't really care about that. If you've ever written code for older or bigger ARM processors, you probably know that the real or the original ARM instruction set is a fixed width 32-bit instruction set. This instruction set is not supported on ARM Cortex-M devices. Instead, they only support the thumb and thumb v2 instruction sets, so that you have 16-bit instructions, and sometimes with thumb v2, even smaller 32-bit instructions. Now, let's look at a specific processor. And so today we will look, for example, at the STM32 from ST Microelectronics. The STM32 is super common in a lot of devices. And what's nice about it is that you can get breakout boards such as these for like $16 shipped on Amazon and so on. And so if you want to play around with chips that are very well supported by open source toolchains and so on, the STMs are really easy to work with compared to some of the others. And basically, this chip has a lot of peripherals integrated. So we have general purpose input outputs, which is basically just a pin. So one of these gold small pins on here, and you can do with those whatever you want. You can turn them on, off, and so on. It has hardware support for serial, I2C, and so on. And if you go on the STM32 F4, in this case, website, you can see that it has a lot of stuff such as CAN bus, a camera interface, SPI, and so on, and that it runs at 180 megahertz. You can also see that it only has 512 kilobytes of flash memory and only 128 kilobytes of RAM. So there's not a lot of space for stuff on there, but it still is able to drive a lot of different things. How are these peripherals such as I2C or the camera interface implemented? Basically, if you check the datasheet of the STM32F4, you can see that the pins on the device are organized in ports. So for example, here I've highlighted port A. And we can configure each pin of these ports. In this case, port A has 16 pins, to be, for example, a general purpose input output, and then we can blink an LED. So we would set it to output and then turn it on or off and so on. Now we can also switch the mode of these pins to, for example, I2C, which would allow us to drive a display and so on. And we have a lot of these ports. For example, on this chip, we have port A, port B, and port C. And notably, not always all pins of these ports are available. So for example, depending on how you configure the chip, the pins on the left might be used for the clock instead of being used for general purpose input outputs. Now, how do we talk to these peripherals, given that we don't have an operating system that we can use to for example, say, hey, open a file, or hey, turn on the display? This is done using something called memory mapped peripherals or memory mapped I/O. Basically, you have your flash, your RAM, and all your peripherals in a flat memory space. And so, for example, your flash on the STM32 will be at hex 800, your RAM will be at hex 2000, and your peripherals will be at hex 4000. And if you want to find this for a specific processor, just go into the datasheet and search for memory map. And that will bring up this nice diagram going into a lot of details on which address ranges are for which peripheral or for flash and so on and so forth. And for example, if we zoom into the lower part right here, we can see that the flash memory of our processor starts at hex 800 and that our RAM starts at hex 2000. And if we go back, we can see that there's one big area reserved for peripherals, which are extended on the right side. And these APB, AHB, and so on just are different buses that are in the chip. We don't really care how this works or what they do. But if we search in the datasheet for example, AHB1, we get another memory map for all the things that are on this bus. And so, for example, in this case, on AHB1, we can see that all the GPIO peripherals, so all the things that we need to turn on and off an LED or so, are on AHB1 and start at hex 4002. And so, for example, GPIO A is at just hex 4002.0000. And if we go into the GPIO register part of the data sheet, we can see that basically there are 32-bit wide registers in the memory that we can use to control it. So for example, if we want to control the mode of this of a GPIO, we just go to the address offset 0. So for example, we know that GPIO A is at 4002 plus 0, and then we have the address of this mode register. And we can now adjust the mode of whatever pin we are interested in changing the mode of by just writing to all of these 2 bits. And you can see down here, if we set mode R0, for example, to 00, it will be an input. If we set it to 1, it will be an output. We have 10, which is alternate function mode, which we need to use if we, for example, want to use I2C or so. And then we also have an analog mode where we, for example, can read analog data such as voltages and so on. Now, let's say we want to set a pin to be an output. All we have to do is set the least significant bit of this address to 1. And so, for example, we would just write 1 to hex 4002. Now, to turn this pin on, because so far we've only set it to be an output, we haven't turned it on or off yet. For that, we need to use the output data register. And again, we have the output data register. We can see that it has, for each pin in the port, we have 16 pins per port. We have a single bit that we can set either to 1 or to 0. And we again can calculate the address. So this register would be at hex 4002 and 14. And if we want to turn on pin 0 and pin 1, we simply write the least significant bit and the second bit just by writing, for example, 3 to this port. And if we want to turn it off, we just write 0. Now, how do we analyze a firmware in Ghidra? So basically, I've created a small crack.me. If you're in the Slack channel, you will find it there. You can download it. And if we drag this file into Ghidra, we get the import dialog. Now, if you would load a regular binary, so for example, if I were to load, just let's say the copy executable, you could see that Ghidra would detect it as a Mac OS X Mach-O binary. But in the case of a bare firmware, it's just a random binary file, and Ghidra doesn't know how to analyze it and how to load it. And so if I drag it in, the format will just be raw binary. This means that we have to tell Ghidra about the language that this file is written in. And in our case, this is a firmware for these STM32 breakout boards. And so in our case, I know that we are loading a Cortex firmware. And so I have to open the language dialog, type in, for example, Cortex. And there are two options here, big endian and little endian. Now, in theory, there are Cortex M processors that are big endian, but in the wild, you will see that basically they do not exist. Like nobody will be, basically you will never encounter a big endian Cortex M chip, most probably. And so we just select little, double click it, hit OK. And now we also need to set the load address. Now we just saw in the data sheet that basically there are, if we go to the data sheet of this chip, the flash memory is at hex 0800. Now we know that our firmware will probably be loaded into flash, and so let's set the load address that Ghidra will use to hex 800, hit OK again, and double click this file. Now, oops, this is coming up on the wrong screen. Now, Ghidra will ask you whether you want to analyze this file. Now, we absolutely do not want to analyze this file yet, because we first want to finish setting up Ghidra to know about the processor we are using. And so we hit no right here. And then we go back to the datasheet of our processor, and we can see that the flash memory is at hex 0800. Our RAM is at hex 2000. But we also see that at hex 0000, that these addresses will be mapped either to flash, system memory, or SRAM. Now, in most cases where the firmware is regularly running, this will be mapped to flash, and so we have to make Ghidra aware that our flash is not only at hex 800, it's also at hex 000, and we also want to make sure that we have our SRAM memory block mapped and so on. And so in Ghidra, you can do all of these things by going to window, memory map, and it's coming up on the wrong screen. And here we can see that our flash, the binary we just loaded, was loaded at hex 800 and so on. And we can create a new memory block. And so, for example, we're going to call this flash mirror. It will be at address 0. It will have the same length as the flash that we just loaded. So 2DOC will be executable, and we will initialize it with the file bytes. So it will have the same contents. We hit OK. And now we have that. Now we also want to create a block for the RAM. So we have our RAM. It starts at hex 2000. And let me check the data sheet. How long is the RAM? It goes up to 1 FFFFFF. So let's copy that in. Also set this to execute, and volatile. The volatile flag is important in this case because RAM might change under you, so without you noticing. And so you want to make sure that the decompiler is aware that RAM will always can change, so it doesn't optimize some stuff away. And we just leave this to initialized and hit OK. Alrighty, and now we're ready to go. Now we can actually analyze our file. And so I'm going to go to analysis and hit auto analyze. And now with firmware, the problem is that it doesn't have a structure like an entry point or so in most cases. So for example, if you load an ELF binary, it has a defined entry point, and then the entry point will jump to your main function and so on. We don't really have that in firmware. We often have a reset vector of which we know the address. We often have interrupt vectors where we can guess the addresses and so on. But Ghidra also has an analyzer called ARM Aggressive Instruction Finder. And this one is really, really useful because it basically allows you to, allows Ghidra to try to find instructions anywhere in the binary. And so it will just go through the binary and see, oh, does this look like ARM code? If yes, it will mark it as code. And so this is really useful. And so let's check it and hit analyze. And we can see on the bottom right, a lot of stuff happens. And we can see a lot of colors changing here on the right side. And that's already it. We are done. And and before we start analyzing it, I want to show you what this crack me actually does. I should have done this earlier. Apologies. So basically, I've put a small crack me on this device, and if I hit reset, you can see it says hack in the box, bare metal crack me, enter the correct combination of signals and press the button. And if we just press the button on here, it will just say unlock criteria not met, try again. And so our goal will be to reverse engineer this check. And oh, I'm just got a question. So we just hit the button, we can see unlock criteria not met, and so we want to reverse this crack me and figure out what exactly is going on and what does it want us to do. Now we could go, for example, to address 0, and we can see the full reset vector here. And so so we can see that on reset, our CPU jumps to this function, which does something and so on. But in a lot of cases where I look at firmware, I try to figure out what would be the best point to figure out where to start. And in our case, we just saw that it has some strings. And so let's see where are those strings used, and that will probably bring us very close to where we need to look to reverse the crack me. And so let's go to the strings window. Just click on window, and you have defined strings. And you can see, indeed, we have the enter the correct combination of signals. We have the flag, which unfortunately in the binary we got is censored. We have the string we just saw. And you can also see that these are here twice. This is because we have the flash mirrored, and so it will be twice in memory, once at 000 and once at 0800. So let's just click on one of these strings and see if we get any references to it. And here in the listing view, you can see that indeed our string HITB bare metal crack me is used at 2 addresses, which are actually the same. And we can just double click this to jump here, and we get into this nice function where we can see, oh, our string is used, enter the correct combination, and then we also see the success message and so on. Now, when I reverse engineer something, I really like, let me answer a question on Slack real quick. HITB lockdown C. Apologies, I'm just trying to do this. Alrighty. Okay, and so if I see this and I know this string is output to the serial console, I will just blindly call the function that I will just call it, for example, probably serial print, because, whoops, let's fix the typo, just because it looks a lot like this is probably the function that prints something on serial. Now I could go ahead and click on it and see if this is actually true and so on, but I mean, do you really have to? I'm a hacker, I'm lazy. But let's still go up and see what these functions do. Maybe we need to know. And so here, if we click on this, we can see some strange numbers going on, and we can see that this basically will write something to 4002.38000 or so. And now what we could do is go into the data sheet and figure out what's at 4002.22. What was the full name? 4002.38000. Oops. 3800, where do we have it? Here, and we can see this sets up the RCC, which is the peripheral clock management and so on. But the problem is, if you do this over and over and over again and manually see a number, go back to the data sheet, figure out what it does and so on, it gets old really quickly and burns a lot of time. But luckily, there's something called SVD files, system view description files. And these are basically files that contain a description of all the peripherals of the chip. And so, for example, in an SVD file, we would have the address of our GPIOs, we would have the address of the UART driver, and so on. And I wrote a script called SVD loader for Ghidra, which you can find on GitHub, which allows you to load these SVD files. And what's nice is that, for example, Kyle gives us SVD files for hundreds and hundreds of chips. And so if we go into Ghidra, I'm just going to call this, as we know, RCC something, and go back to the function we came from. And for example, here we see some more addresses that are probably in the peripheral range, but that we don't know yet. But if we load the script called, so I just go to the scripts window, level down security. If you don't see your script in this list, you have to add it to the script path. So click this button and then add whatever directory you cloned SVD loader to. And then we just double click it. And it will ask us to select an SVD. Now I have a lot of SVDs. There's this nice Simsys SVD GitHub repository where you can find hundreds of different, or almost thousands, I guess, SVD files. And in this case, I even have an SVD file for the STM-F446 that I'm using on this board. And so I'm just going to double click this. And it will take a while. I should have put a Jeopardy sample on here. Oops. Oh, hello. There we go. Okay, took a while. I'm not sure why. But anyway, now you can see that the red address here turned into GPIO-C. And so now we know that whatever red address this was is now GPIO-C. And if we, for example, check out what's behind this, so we can see that this data here that is put in this function is actually a pointer. And so if we hit P, we can convert this into a pointer and we can see, oh, okay, this configures GPIO-A. And if we do the same here, we can see this is probably a pointer. This configures the UART and so on. And now without even touching the data sheet, we already know that, okay, this is like something. So USART is the serial port. We know that this is also USART something, so we can call it USART something too, and so on. I'm not going to label all of these because we don't really need it. And then we also have GPIO-A, so this probably configures the GPIO-A port for whatever. And but let's go back to what we actually want to reverse, which is the CrackMe. And we can see that the actual CrackMe is happening in here. So we can see enter the correct combination of signals, and then this happens. Now let's see what's behind this. If we double click a data point, we jump to it, and we can just hit P to convert it to a pointer, or you can do a right click and set data to pointer. And we can see that this actually points to the GPIO-C PUPDR register. Let's see what exactly the PUPDR register is in the data sheet. Yeah. So there are always two documents for a chip that you need to be aware of. There's the data sheet, which is 200 pages. And then there's the reference manual, which is 1,300 pages. And so it's huge. And so let's just search for PUPDR, and we can see, okay, PUPDR just sets the pull-ups and pull-downs on the GPIO. That's some electrical stuff we are not really bothered by, but let's just call this GPIO-C pull-ups. And we can see another write here, this time, oops. And we can see that this sets GPIO-C to 0. Now, if we go back to the datasheet, we can see that this basically just sets the pin direction of GPIO-C to be inputs, because we earlier saw 2 zeros mean inputs. This just sets the entire GPIO-C to be an input. And then we can see that the pull-ups are activated. And so a nice trick, if you see 0xAA but want to see it as binary, is that you can, in the listing view, right-click it and convert it to binary. And we can see, okay, this for the 1, 2, 3, 4, for the first 4 pins, this will enable pull-ups. If we go to the datasheet, we can see this. Pull-downs. So it basically sets for pin 0, 1, 2, and 3, it sets it to be a pull-down. And so we know what this does, and we can go into the actual loop. Now, the first variable here is PUVR1. And so let's track back and see what this does. Again, we can, we can convert this to be to a pointer and name this, okay, this is the GPIO-C input data. And this will basically always hold whatever input state we have on GPIO-C. So if we go into the datasheet again, we can see that IDR is the input data register. And if we have a pin configured as an input, we can just read the single bits to see whether, for example, the button connected to it is pressed or not pressed, and so on. Now, to make this a bit easier, I can tell you that this basically just reads the button, and so it basically waits for a button press. And because, as we saw earlier in the console, if we press the button, we get the try again message, and so this just waits for the button. And if we, oh man, what's going on here? Sorry, my computer is a bit laggy here. Here. And so, unlock criteria. Let's name this unlock criteria. And we can see that it waits for the button press, and then it checks a condition. And if this condition is not met, it says, oh, unlock criteria is not met, please try again. And we have to start over. And so our correct me content is in this here. And this basically just reads the GPIO-C input data and then checks whether the least four bits of it are equal to 2. This basically just means that what we have to do is somehow on the GPIO-C input set the second pin to true, and suddenly our correct me will be solved. And so, for example, I can do this by using a simple jumper wire. So I've checked in the datasheet of the board where my pin 2 is, and I just apply some voltage to it, press the button, and we've reversed the correct me. And so now this is obviously a very simple example on how you can reverse something in Ghidra, but this can be done on a lot of things. And so, for example, if we check a different processor, the LPC1334, it has something called the CRP, which is the code read protection. And so this basically is a piece of code that checks whether the debug interface that gives you access to, for example, read the flash, read the RAM, and so on, is available to be used, or whether it's locked down. And so, for example, on a hardware wallet, you would try to lock this down, and on a dev board, you would leave it open if possible. And what's a nice attack is if we could somehow re-enable this code read protection. And so this code read protection on the LPC is implemented by writing to a certain address in Flash. And so again, we can check the reference manual. And basically, the code read protection works by checking whether a specific pattern is in Flash. In this case, it checks address 2FC. And so what I've done is I've loaded into Ghidra the boot ROM of the LPC chip. And if we go to the address 0x2fc, and I've already set up the memory maps and so on, you can see this. You can see this right here. I've already set up flash SRAM and so on. And you can see that we can actually, by loading the boot ROM, we can see where this code read protection is read. And so, for example, we can see, if we click here, we can see that there's some code that works on the code read protection and so on. And we can start reverse engineering the boot ROM and try to figure out how exactly does it work, how can we potentially bypass it, and how can we find vulnerabilities. And now this would take a lot of time, but there's a nice other trick, because we now know, as we have the boot ROM, which is executed on each start of the chip, as we know that it's read from flash each time the chip boots, we can do something called a glitching attack or fault injection attack. And so basically, if you look at the power supply of a chip, if you manage to somehow interrupt the power supply for a couple of nanoseconds at a very precise time, you're able to change the behavior of the chip. And so this is called glitching. And what you can do with it is, for example, skip instructions or corrupt flash reads and writes, corrupt register writes, and so on. And what we can do, and as we know that the chip is reading this from flash on every boot, this means that what we could do, oh, my camera just died. 1 second. This means, I hope you can see me again. This means that what we can do is basically try to do this glitching, this voltage glitch at a very precise point in time on every single boot. And I'm going to give over to my colleague Dmitry, who will explain the details of that. So Dmitry, away you go.
Yeah, perfect. So yeah, now we're going to take a look at glitching. And so the specific device that we're going to look at is I have in front of me on this table. So let's switch to that. So we're going to take a look at this guy right here. So this is an LPC 1343 development board. And we'll actually be triggering the glitch using this right here, which is an RD, a Digilant RD FPGA board. But let's just briefly take a look. So I'm going to share the slides just with, oops. Sorry, it's in the other corner.
I'm assuming they will be right back.
Sorry, I unfortunately forgot to give Chrome the rights to share my screen, so let's try one more time. So I'm going to share my screen, and hopefully, let me just check really quickly. So everything else looks good. All right, so let's just take a quick look. So I'm going to switch to Keynote, and let's just take a quick look at this. So basically, this is our board right here that we're going to take a look at. And like Thomas already explained, so what we want to actually do is glitch the boot ROM. So with something like with Ghidra, we can actually go and we can analyze and find vulnerabilities in this boot ROM. So like Thomas said, it turns out on this specific microcontroller, it only checks the value one time during boot, and so that actually means that it's very easy to trigger. So all we need to do is reset the board. We can perform a glitch, which we'll take a look at in a second, and then we can recycle everything and try again. And during every single boot up of the microcontroller, we can actually look and check, is it working or is it not working, etc. So basically, so basically, there's a couple. I mean, in terms of the glitch theory, a lot of people ask about this. So you have to think of overclocking as the example that I always use, and I think especially hackers are familiar with overclocking. So if you want to run something at a higher frequency, it needs more voltage. So we're going to do the exact opposite. We're dropping the voltage, which means that running at the same frequency, the system actually becomes less stable. So, I mean, that's the gist of what we're doing. And so what does that mean, less stable? Well, data is actually going to get corrupted. So that means that, for example, instead of reading on a 32-bit bus, instead of reading, let's say, all Fs, it's going to read an E somewhere, or instead of reading all zeros, it's going to read a single bit that's 1. And depending on what the actual comparison is that's happening in the microcontroller firmware, in the boot ROM, that'll affect essentially the security of the device. So in this case, I mean, Thomas already said it, and I said it a couple times. It's going to be just a single check that happens. And unfortunately, I mean, this guy boots off of an external, off of an internal RC oscillator, which has the disadvantage that we can't control it somehow externally, but fortunately it'll still work, but we do have to make some modifications. So basically, this is what we're doing. We have a reset that happens at some point in time. That's the end reset signal that's green. And at some later point in time, what's actually happening is we're going to trigger the glitch. So we're going to drop the voltage for a very short amount of time and basically go from there. So how does this look like in practice, specifically with this chip? So it turns out the security is based on a magic value that gets stored at 2FC. And so this is something that Thomas was already showing in the actual manual for this microcontroller. So it turns out there's exactly 4 values that apply security to the chip, and those values are, and this is not a joke, 1, 2, 3, 4, 5, 6, 7, 8, 8, 7, 6, 5, 4, 3, 2, 1, etc. If it's not one of those values, then it treats it as unlocked, and you can verify this just by reading the document that NXP will provide for you. So basically, you have to think of it like 4 values lock the device, and since we're talking about ARM 32 bits, that means 2 to the 32 minus 4 values unlock the device. So chances are very good that we can actually unlock this device. So to secure the device, the user, again, has to explicitly write a specific magic value. And since 1, 2, 3, 4, 5, 6, 7, 8, or 8, 7, 6, 5, 4, 3, 2, 1, since these patterns are not valid ARM opcodes, I mean, I guess the assumption is that NXP made when designing this is that you'll never accidentally put code there that will lock the device. So let's take a look at what it's like to talk to a bootloader, because we're talking about the bootloader, the boot ROM. So basically, if you look very carefully, it'll say so another thing that you commonly have is that you might actually have more than one bootloader. And if you ever given the choice, you always pick the most simple interface available to you. And in this case, that happens to be the UART interface. So that means we can just connect with a serial console and talk to the bootloader and play around with it. And that's basically one of the first things that we'll try to do. Then we can go and set the security of the bootloader, and essentially then we can go from there. Okay, so this, again, I just shown this slide just because this is what we actually have to implement on the FPGA. So I'm not going to go into a huge amount of detail on how that's done, but basically we need to generate a delay and a width. And so essentially after a certain amount of time, i.e. the delay, which is a 16-bit value, we need to do something for an 8-bit value, so 0 to 255. And these are all units. It's units. These are clock cycles of the FPGA. So what we're actually doing inside the FPGA is we're building counters that actually control all of this. And how do we actually switch and manipulate the voltage? Well, you can grab an analog multiplexer like this one, the Max 4619. And so I have VCC and V glitch. Those are just 2 arbitrary input voltages. I mean, you can see this device actually normally runs at 3.3, but we're taking it down all the way to 1.6. Because why do we take it that low? Because it's less stable at that point when we start to glitch it. It's already running at the bare minimum, and we can go from there. So let's pretty much get into it. So last thing, I'm not going to go into a huge amount of detail, but this is as simple as the logic is inside the FPGA. So we have the command module, which is the module that actually processes the commands that we can then send from a nice scripting language like Python. So we'll actually use Python to configure the FPGA and configure the glitch. And then we need to reset the board. After we reset the board, we need to wait for a delay. And after the delay is up, we can pulse and toggle the voltage. So let me switch back. Oops. Let me switch. Oops. Oh, sorry, my escape wasn't working. So let me switch to my. Let me switch to the camera. So let's talk about this one more time. So here's the FPGA board. This is the microcontroller board. So and we're going to be using a power supply, and this is something that I already had a chance to rig up, which is a multiplexer, which we'll discuss in a second. But basically, this is just going to match the schematic that I had on the previous screen. So let's take the first thing that we can do is we can just try to talk to the bootloader on here. So there's one modification that we have to make at the very beginning, which is we actually have to be able to get it into the bootloader. For that, we need one more connection on this board, and this is actually described in the data sheet. So let's go for it. So let's modify it. So I'm going to grab my soldering iron, which are over here to the side. So we'll just need one for this part. And I'm just going to add a connection. And we'll need a male to female wire for this. And I'm just going to add a connection to the microcontroller right here. And this connection, like I said, it's documented if you read the data sheet. And it's going to be the 4th pin over here. It's going to be the 2nd column over and the 4th pin. And this pin we need to connect to ground. Fortunately, we have this JTAG connector right here. And that'll actually, this JTAG connector has almost all the signals that are ground. A bunch of them are unused. So we can actually use that and connect the signal there. So I'm going to unplug it, obviously, because you can short something soldering. So I'm going to leave it there. And so I'm going to solder this connection. So 4 and 2, I'm just checking one more time. And should be this one. Looks good. So obviously, if you have the choice, always use leaded solder for this kind of stuff. Oops, sorry. I think the other one's the one that's heated up. Yes. All right, so that connection we're good to go. So now all I need to do is to connect this to a ground pin. And like I said, fortunately, almost everything is a ground pin on here because we have this JTAG connector, and on an ARM JTAG, most of the signals are ground. So I'm just going to pick like number 4 over here, and then we can test it. And we can test it by connecting it to power again, and also setting the jumper. So we can see now it's in a bootloader mode. How do I know? Because the default firmware that's currently on the board, which would normally run, would toggle the LEDs. So that's not happening. So we know we're probably in the bootloader. So now what we're going to do is connect the FPGA and actually try to talk to the board. So let's take a look at how that works. So on this board, on this FPGA specifically, what we have is so we have an FTDI right here, which is connected to the FPGA, which then we can implement logic to talk to any of these pins. But I've already configured the last 2 pins on this header to be to essentially pass through the signals that are normally connected to the FTDI directly to this board, which means that I can directly communicate with the board once I have it connected there. So I'm going to grab 2 more connections, 2 more male to female, and connect them. Connect them up. So it's going to be on pins. So these, I'm going to connect them to the UART pins of this guy. So the TX and the RX of this guy, I'm just going to connect right here. And then I'm actually, so wait, I might have the same problem. So I'm actually going to switch to another machine. So let's see if it works. It looks like it's working. And here I have VMware running. So which means that I should be able to log into this VMware. If I don't mistype the password. All right, so basically right now we can actually connect using Picocom. So if I look, there's Picocom. I can connect over to this device and we can actually try to talk to it. So what's the problem? So I think I need to, let's reconnect the FPGA just in case. Let's make sure we connect it to the VM. And we have to now, unfortunately, do one more thing, which is we have to flash the FPGA. So I'm going to auto-connect to the FPGA. Let's do it. So we're going to connect. We're going to... So it's going to output into here. And we're going to program it. And then we can actually play around with Picocom. Okay? So I don't have it on the screen, but if you were to read the documentation, the first thing that we actually have to send the board is a question mark. So let's try that. And if it doesn't work, that means that we might have TX and RX wrong. So let me just check that I am typing it correctly, just in case. So let's check if we have TX and RX wrong. I'll restart this one more time. Let's try it one more time. No, so it's not working. So let's swap these two. So I'm going to swap these two. All right, so there we got synchronized. So now if I actually type synchronized without making any typos. So if you look really closely, let me make this larger. If you look really closely, what you will see is the S and the Y and this bottom line, the S and the Y and this bottom line are going to get overwritten just because the board doesn't send a new line back for whatever reason. So I'm going to type synchronize. So it sent back OK. So that command was fine. So now I need to give it a frequency for the crystal. I mean, this is also just straight from the datasheet. We'll tell it 10,000. This doesn't really matter, but we need it as a command to actually initialize the bootloader. Okay, so it's happy. So now I can actually go ahead and read and write to send read and write commands. So in this case, the commands, when it returns something, they'll actually be UU encoded. So ignore that for now. I mean, it's not super important. It's just the encoding that NXP selected for this chip. So I'm going to send R04, and you'll actually see I get something back. So I'm actually able to read and write this chip. So this chip is not currently locked. So that's a problem. So let's do it one more time. So in the meantime, I'm going to quickly, I'm just quickly going to switch screens again. And this time we'll use terminal. So what I'm going to do is share this one now. Actually, let's do application window. Let's go to oops. All right, so let's go to this one right here. So let's share the terminal window. All right, so here's the terminal window. Now all I'm going to do, so the cool thing about this bootloader, I told you that there's a UART bootloader. There also happens to be a USB bootloader, and the USB bootloader is super nice for the USB bootloader. So wait, let me see. The USB bootloader is super nice for flashing this guy. So what I'm going to do is I'm going to hit reset, and now if I actually look, if you know macOS, then under volumes we'll see we should see this guy pop up. So let's do it one more time. Let's see it. So it's still not there. So let's just go to volumes. So oh, it actually is there. So it's called CRP disabled in this case. So what I can actually do if I go back is if I copy, for example, CRP with binary, I can actually go to volume CRP disabled, and I can overwrite firmware.bin. So now if I do that and I hit reset one more time, what actually happens on the host is this will come up and this will no longer be CRP disabled. This will be CRP enabled. And if we actually try to read the firmware that's on there now, so I probably should have shown you before, you can see everything zeroed. So clearly the security has been implemented correctly on this chip. So you'll see we can't read any values, even though I just wrote a binary, and trust me, this binary is not all zeros. It's not letting me see it. So now if we switch over to the other machine again, so if I stop this guy right here, if we switch over to the other one and switch back to VMware, and now we do the exact same thing. So I'm going to reset it. I'm going to reconnect the connection that I need to be in the UART bootloader. I'm going to send a question mark again. We can see synchronized. I'm going to type synchronized. I'm going to do 10,000. And so right now, CRP1, it basically enables all the security, but the bootloader, the boot ROM code is still there. So we can actually communicate with it, debug it, play around with it, etc. Don't ask me. I mean, technically, we'd still be able to update the firmware, but we can't read it off of there. So let's pretend this is some super important binary and we actually want to pull it off of this device. So let's try to do it. So I'm going to do R04. And if you look, we got a 19 code as our return value. So that if you look before, the value that we got was a 0. So if you look up in the datasheet, a 0 means a command success, and a 19 actually means, so this value right here, the 19, if I could click, the 19 at the beginning of that line, what it actually means is where we were unable to read because this chip is actually has protections enabled. So next step is actually to modify. Let's talk about the strategy real quick. So I have a script already ready. I have the logic ready for the FPGA as well. So if we actually try to run the script that I have right now, so I have this Python script right here. So let's try to run it. So you'll see what this Python script is actually doing is it's running against the binary there, and it's just checking. It's trying to reset it. It's checking like, are you good? Are you good? Can I read? Can I read? And you'll see that every single time it's getting values back where the device reports back that it's locked. So it's not working. So we need to make a modification. So we actually need to implement the glitch. So let's do that. So we need to make a couple more modifications to the board. So I'm going to stop sharing the screen, and let's go back to the camera. So to the actual boards. So we need to make a couple more modifications for that. And let's do them. So the first thing that we're going to do is we're going to remove any filter capacitors that we might have on the board. So let me just make sure that the video is good so that everyone sees it. So I'm going to disconnect everything. So we need to make a couple more modifications. So first modification is going to be, also let me make sure my irons are hot. The first modification we're going to make is we're going to remove 2 capacitors. So we actually have a capacitor right here. And this is, let me see if I can get just a little bit more zoom. No, unfortunately I can't. So we have a capacitor right here, and we also have a capacitor right here that we want to remove. So for this, I'm just going to move this out of the way, and I'm going to move the other cable out of the way. I mean, for this, if you're asking me, the easiest way to do it is always just to use 2 irons for removing the capacitors. And after we do that, we actually have, these shunt pads, which we have on this board right here. So you'll see one's labeled 3.3 volt IO, and the other one's labeled 3.3 volt core. So these are 2 pads. If we cut with using, for example, a scalpel or even a Swiss Army knife is what I usually end up using. If we cut them between there, what ends up happening is we've disconnected this entire chip from the outside world. So that means we can now directly inject the voltage onto this board. So if you wanted to, you could actually go and connect this to a breakout board. So I can't see. I thought I might have some right here, but I don't see them off the top of my head. But or I don't see one right away. But basically, it turns out it's easier to modify this board than it is to actually desolder the chip, put it onto a blank board, and go from there. So that's what we're going to do. So let's do it. So I'm going to take a knife real quick. So let's also use the multimeter that I have right here. So we're going to go into continuity mode. Let's check the connections that they're still there. So between this guy and this guy. So you can hopefully hear the beep on the stream. So it's beeping, which means there's a connection there and there's a connection there. So now let's cut through those, and we'll have separated the power supply from the rest of the board. So I'm just going to grab the short knife like this one. And so people that have tried playing along and doing this as well, people always ask me, how do you know if you've done it correctly? And the answer is, if you hear a crunching noise, then you're probably deep enough to have cut through the wire. So you can actually, I mean, you can't feel it on the stream, but trust me, you can feel the connection right there. So let's take a look. So I'm going to leave the knife right there. And now let's take a look with our multimeter again. Let's make sure there's no more connection there, because now we'll have separated our power supply. So it sounds good. So if I tap this, there is a connection, but if I tap the pads, there isn't. So one more time. All right, we're good to go. So now we can actually solder 2 wires onto there and make all the necessary modifications. So let's remove the capacitors first though. For that, I'm going to make sure both my irons are hot. They both seem to be warm. And so I'm going to use 2 irons for this. You should always get 2 nice irons. And then it turns out that stuff like this is super easy. So I'm just going to warm it up on both sides and remove it that way. And same thing on this guy right here. Just warm it up on both sides and it should come right off. So we're good to go. So now I remove the capacitors because, of course, anyone who remembers their university lecture on capacitors work as filters as well. And so that's why we don't want them. That's why we want to get them out of the way. So capacitors removed. Let's try. Now we need to solder 2 wires onto there. So fortunately, while Thomas was doing his part, I've already prepared the wires. So I took a regular jumper wire. I cut it in half. And basically braided them just simply by twisting. So twisting like this. And now they're pretty much good to go. So for that, I will still need one of the irons to actually be able to prepare this. And I'll also need the solder, of course. So if you're doing something like this, it's also always nice to have flux, because flux always makes your life easier. So I have this nice rubber pad. So we can just prep it with some flux. I mean, it doesn't really matter if it's too much. If you pour a little puddle, it'll be fun. So I'm also going to prep the places where I'm going to solder it in a second. And let's go for it. So I'm going to go like this, and I'm just going to prepare my tip. And then I'm going to take one of these guys, and I will just get this entire edge filled with solder. Okay, and you saw I had so much that some of it even fell off the tip, but it doesn't matter because we just need solder on there. So now let's do the second tip, the tip of the second wire. And so if you ever watch, I mean, if you solder enough, you'll also eventually, you might end up noticing that sometimes the solder, it doesn't latch onto, it doesn't hold on to the end of the braided wire as well. So it's usually a good idea if you have the chance to cut off the tips, because usually there's no solder there. So that's what I'm also going to do. So again, for this, our trusty Victronics Cyber tool. So I'm just looking for the scissors. So there we have the scissors. So I'm just going to cut off a little piece of this. I'm going to cut off a piece there. And I'm also going to cut off a piece here. Okay, and so now, we actually want to mate this on here. So let's try it. So we're going to create a pad. So I'm going to hold this onto here and try to put some solder down to create a pad. And I also need a connection on this other pad. So exact same strategy. So you see, I'm not trying to put too much solder down, just enough for me to be able to connect everything there. So let's go. And so how do you know if it's there? If you can drag the board by it, then you're probably good. And finally, let's do the second one. So I have to bend it a little bit just because I want to make sure I don't have any excess tension there. And that wasn't good enough. All right, but the second one was. So last check, let's check if it beeps, because we don't want to short, otherwise it'll be hard to actually perform the glitch. So, wrong mode. All right, we're good, because you can see, so I'm holding the one side of the wire. I'm holding the probe there. And I'm also holding, connecting the probe to the other side. So if I touch the pad, it's good, but the other side is not connected, and this side's good, and the other side is not connected. So we're good. So basically, just with that quick modification, what we've eliminated is all these electronic components that are otherwise on this board, which would have just made our life slightly more miserable. All right. So now we need a couple more connections. So let's take a look at this guy right here. So all this is, I had this in the slides, is a multiplexer board. So if you look really closely, let me try to unwind it a little bit just by moving it like this. So here's the multiplexer board. So if you look really closely, you'll quickly realize that almost everything is actually connected. So almost everything, so all these dark and more or less neutral colors, except for the green wire, are actually connected to ground. So I have a bunch of ground connections here, and so those are just ground. So whenever you have an analog device, you want to make sure that you don't use any of the inputs that are not part of the circuit, essentially. So everything that I'm not using, I'm getting rid of. So I still need to connect the TX and RX of the board. So I still need to connect the TX and RX. And so I'm going to connect them right there. That's where the TX and RX are exposed. So these orange wires I'll want to connect to the actual output of this multiplexer. So if you look, I mean, this is, if you look, wherever we have this yellow wire is where the output is going to be according to the schematic of in the data sheet for this multiplexer. So what I actually need to do is I want to make sure that I don't have any bad connections, i.e. I want to make sure that I don't, or I want to make sure that I don't accidentally break the soldering work that we just did. So I'm going to grab let's grab two male to female jumpers, and we're going to connect them right here. So we're going to connect them to this guy, and we're going to connect them to this guy. Boom. Let me zoom out a little bit just because it's getting intense. So we have these two connections going on now. So these yellow wires are our actual voltage signals. So I'm going to connect them to where we have the yellow wire over here. And let's connect the second one as well. All right. So we should be more or less good to go. So one more important thing is, of course, we need ground. So where's, let's check ground on this guy. So 1 second. So for that. All right, let me do this. All right, let's try to connect the ground. I just need one more male to female. Let's go for it. And I mean, we can also take a look down here. So the ground, I'm pretty sure it's the outer one. That's the ground plane. if I remember this board correctly. So let's connect this guy to ground. So we can also connect to the FPGA. So we have ground pins over here. And so we should be good to go. And now we still need to connect this guy right here. So what this guy is this is actually these really nice Chinese power supplies you can get nowadays. So everyone in my family would ask me why I don't throw away the Linksys power supplies. So you just feed a barrel jack into this guy and you can essentially generate any voltage you want. So let's just, for now, for testing purposes, let's set the voltage to, for example, so I actually have it, if you look up top, you'll see I have 1.62 volts as the limit. And then we also have a current limit of 20 milliamps set. This is more than enough. So let's set the output to go high. And we can see no short because the current, there's no current. So let's connect these guys. So I'm going to connect one to ground, just like we did with this guy. And I'm going to connect the second one to, let me take a look. So I'm going to connect the second one to this guy right here. So this red cable is going to be our second input. And afterwards, we should be good to go. All right. So hopefully it focuses now. So everything's connected. So we should be good to go. So power supply, let me turn it up. Hopefully you can see it. There we go. So hopefully you can see it there on the screen. So I'm going to just a quick test, sanity check. So we can see it's all good. Power supply is good, so nothing shorted. There's no current going through. So last sanity check I would actually do is to take the multimeter and check the voltage. So let's try to do that. And right now, the voltage should be whatever we're outputting from the power supply. So let's take a look. So for that, I have this guy right here. Let's connect it over here. And let's connect this one over here. So it's slightly off the screen. Unfortunately, with my lamp, it's coming off. So you'll have to take my word for it. But we're getting the 1.62 volts on the output. So we should be good to go. So let's connect. We also fortunately have an oscilloscope for this. And we can make sure that everything's working. So first thing I'm going to do is, so one more important step is I need one more male or female to connect the reset. So let's take a look at there should be a reset pin right here. And let's share the screen on our VMware machine. And let's switch over there. And we should be able to take a look from VMware. So the only thing that I unfortunately don't remember exactly, so let's take a look just to be on the safe side, is which pin did I use for the reset. So I'm going to open up what's known as the constraint file. So this is the file that maps signals from one pin to the other. So we can see the next pin, the third pin on this header is the actual reset pin. So I'm going to connect it there. So last thing I'm going to try is, so let's do one more thing. So I'm going to reconnect this guy. We're going to make sure we can program the device. And last thing I'm just going to do is check that the TX and RX are fine. So I'm going to try PicoCom one more time, set a question mark. So right now I don't see anything. So let me make sure it's not the TX and RX being connected backwards. So let's try to reset. Let's do it one more time. This is still nothing. So one more. So here, let me try one more thing. So let me just make sure. Yeah, so this is going to be the ground. So, I see the issue. We actually lost this connection right here. So let's fix that really quickly. So unfortunately, our irons both turned off. So I'm also gonna unplug this guy, and I'm also going to unplug this guy just to be on the safe side. So let's do it. Let's fix it. So which one did we lose? We lost the one over here. So now the wires are getting in the way a little bit. So let me turn this around and do it from here. All right, but unfortunately, so let's try it one more time. So let's get this guy. Let's connect this guy over here. Let's boot this guy up. So this guy's good to go. So now let's reconnect the USB. USB should be good to go. So we're reconnecting this guy to this VM. Let's set it to remember. So it's complaining that the hardware shut down. Let's try it one more time. Program. And so that part worked. So let's try PCOM one more time. And I'm going to send a question mark. So nothing. So maybe the TX and RX were not backwards. Oh, I actually see what we forgot one more connection, which was we didn't supply the connection to the power supply. So let me get that. All right. So let's try one more time. And if it's not this, it's going to be the TX and RX being backwards. So let's try one more time. All right, so there we go. We have synchronized. So what does that mean? So all the connections are good. So I'm actually powering it at the lower voltage, which I showed you before on the power supply. And so now we can actually take a look of how this runs and let it run and basically watch the oscilloscope instead. So what I'm going to do is I'm going to connect my oscilloscope really quick, and I'm going to connect it to the output wire, which is going to be this guy over here. And I'm also going to, so I also will need a ground for the oscilloscope. So let's connect that. And finally, so we have the ground good to go. And finally, we also probably want to connect the reset. So for that, we'll also want a ground, and we'll make sure the other signal is blue, just to be nice and matching. So let's connect it. And so let me show you these connections real quick, just because I'll start the Python script. That part is not all that exciting. So I'm going to connect the ground. So let's just use the grounds that we have right here on the FPGA, because they're easy to get to. And finally, we need to connect this reset signal. So the reset signal is this white wire right here. I'm going to be lazy. I'm going to extend this reset wire, basically make it longer. I'm going to add another male to female to it, and that means that in between I can clip on the probe. So let's connect this guy right here to the reset signal. Boom. So should be good to go. So now let's switch to the oscilloscope, and let me actually start the script so that we see stuff. So I'm going to hit Control AX, but I'm just going to start the script. All right, so now let's configure our trigger really quickly. So let's get rid of this guy and this guy because we know there's nothing there. And let's set our mode to auto initially. And let's make sure that, let's figure out which channel we're actually triggering on. So we're triggering off of channel 4. Let's set it to let's do it to channel. Let's do it on channel 2. Channel 2. And so now let's figure out where our level is. So here we go. So it was that. So let's get rid of this menu right here. And we can see the trigger right there. So now if we zoom in, we can see, so the blue signal right now on the screen, the blue signal is the reset signal. So hopefully that's coming across a little bit. So it is, I am moving it around. So let's switch back. I think the compression was killing it. So it was still running. So let's make sure we didn't lose it. So there we go. So it should be updating on the screen. So let's go back. There we go. So it's updating on the screen. So you can see just the little bit of jiggling that it's doing. It means it's actually updating. So let's take a look. So we should also have the glitch signal. So the glitch signal currently, we still haven't connected we're missing one more signal, which is the actual VCC select. So that's on pin 34. So I'll show you me connecting that signal right here. So right now we're going to connect this green wire. We're going to connect to pin 34. So 34 fortunately is this guy right here. Should be this guy on the second header. So let's take a look. So let me just make sure. So yeah, IO 34, so that should be good. And there we go, I already see it. So we're gonna head over to here on the oscilloscope. We're gonna head over to here. And so if you look, the blue signal, you'll see there's a dip, and that's the reset, and this is our actual glitch signal. So you can see right here, so what's happening is the board's power cycling, and then we're dipping the voltage at different points in time and just letting it run. And so you can actually see this going across the screen. We can move this guy down a little bit, make it a little bit bigger, just so that everyone can see it. So you can see the voltage, it's dipping from approximately 1.6 volts to lower, and we're just going across. And so let me just briefly, for completeness, show you what the Python script is doing as well, because once you've seen the glitch actually work on the oscilloscope, you actually want to see the Python script running. So let's go over to here, and you'll see the Python script's running the entire time. So let's even go to full screen. So one thing that you could actually do, so I'm not going to touch it so much, but one thing that you can actually do is you can lower the voltage and just see where the limit of the system is. So I'm going to start lowering the voltage a little bit, and you'll see that at some point we'll just get complete garbage. And so essentially right there, that means we've gone too low on the voltage. Otherwise, we'll just let it run. So usually with this kind of board, the values where it will succeed to glitch the board will be about 5400, something like that. I mean, it depends on the voltage a little bit, but right around that value. Very rarely do you have to run it multiple times for it to actually output something or for it to actually crash. But essentially, you just let it run like this, and eventually it finds the correct position. So I'm going to check the chat, which I haven't been doing during this session. And let's take a look. So, I mean, if there are any questions, I'd be welcome to entertain some. Otherwise, we'll just take a look at this running. So whichever, I don't know what's more interesting, the Python output. So maybe I'll just comment on the Python output really quickly. So the first number is the actual delay in clock cycles of the FPGA. The second number is the width. So that's how many clock cycles we're holding the line low. And we're iterating over this many times in a row and just letting it run until we find the correct position. So very rarely, we might have missed it at the beginning where we didn't have all the connections, but I'm pretty confident this is still gonna succeed. It just hasn't hit the right value yet. So we're just gonna let it run and it will eventually succeed. And this is, so I saw, so there we go. You see expected 1. So what it's actually checking is it's checking the UART output of the device. It's checking the UART output that it gets back from running this script against the device. Every single time it's issuing a read command, and it's checking whether it got a 0 or a 1. Because we know that the case where it succeeds, it will actually return a 0. And wherever it fails, it'll return a 19. But 19, of course, starts with a 1. So that's the output that we're checking. So if I was to connect over Picocom right now, I could do R04. Fortunately, I also have a script. It's called dump.py. So this is just a script which actually converts the UU encoded data and lets us dump the binary that's on there. So I'm going to run it, and you can see we're dumping the binary. It's working. So we've succeeded to boot the chip in such a mode where we've defeated its security, and now we're able to pull the firmware off of there. So if this was, so basically what we just did is we took a device which had no security set, we set the security, and we kind of practiced the attack against this family of microcontrollers, and we did it all in however many minutes I've been going. So essentially we've done our homework. So now if we ever come across an NXP LPC, and I can tell you from experience, this applies to NXP LPC 17, NXP LPC 13. Basically every NXP LPC is susceptible to this because they all share this low-level code in the boot ROM, and this low-level vulnerability that you can find using, for example, Ghidra to figure out what's going on inside of there. And so I can show you the most interesting thing is if I hit Control-C and I scroll back, if you recall, the values that we are actually setting are 1, 2, 3, 4, 5, 6, 7, 8, 8, 7, 6, 5, 4, 3, 2, 1. So in this case, it should be 1, 2, 3, 4, 5, 6, 7, 8 because I set it to CRP1. So I programmed, I put a binary on there that is 1, 2, 3, 4, 5, 6, 7, 8. So if I go to 2FC, we can check which word is actually written to that location. I scrolled past it. So here you go, right here. So you can see at 2FC, we have 1, 2, 3, 4, 5, 6, 7, 8. So even though this device is secure, even though the actual physical contents of flash have the correct value, at the moment of time at which it booted, by playing with the voltage and ensuring that the system booted in an unstable state, what we did is we made sure that the single read where it checks that value in the boot ROM, it read something else. So what might it have read from the flash? Well, maybe it read 0, 2, 3, 4, 5, 6, 7, 8, something like that. Maybe it corrupted the 8. I don't know which bit it corrupted. All I know is that it read some value which was not one of the 4 values that locked the device. And how do I know that? Because the device managed to boot in a state where we were able to get into it and dump its contents. So we somehow corrupted this value at the one point in time at which it gets read during boot. That's like a very short intro to glitching. I did see there's a couple of questions in chat, so I'm going to switch to that really quickly. So let me do that. So I'm going to stop sharing and then switch back to the camera if you guys have any questions for me. So I did see the first question. So let me grab, just because I had Slack open on this machine. So the first question was the 4919. So I'm using I believe it's I always forget, it's the 4617, I think is what I'm using. I'll get back to you in the chat if you, I'm unsure right now, and with the lights I can't read it directly off the chip. But it does have, so the question was, it has quite a bit of resistance. And so the answer is yes, it does have quite a bit of resistance, but this actually isn't an issue for glitching, because all we need to do is to make sure that the power that's actually arriving at the device is so low that it's corrupting it's corrupting the value. All we need to do is to make sure that we're pulling the low voltage low enough to where it fails to read this single value correctly. So even though it has a high resistance, something like a microcontroller, since it pulls so little current, it won't actually have an issue running. It won't actually have an issue with something like this. So not to worry. And then finally, so there was another question. You have the FPGA connect to the reset pin to the power supply via the multiplexer. With a Python script, you interface with the FPGA over UART and vary the delay of the width of the glitch. So yes, all parts of that statement were correct. So what you can actually do with the FPGA, so if I switch, so what's actually happening is I'm implementing on the FPGA, on the actual FPGA, I'm implementing a state machine, which is parsing its command, which sets the delay and the width. And but basically, we have the good fortune of the microcontroller, so the red board that we're actually glitching. This red board is so this red board actually has. So this red board also uses UART. So all we need is UART to communicate to the FPGA and communicate to the microcontroller board. So moreover, in our case, the microcontroller board actually has an additional feature, which is it only uses, because it uses UU encoding, you'll see that there's no binary data that falls into essentially valid encoding. So what that means is you can send data directly through the FPGA as long as it has essentially a non-printable byte in front of it, and then you can process these special bytes to issue commands to the FPGA to basically tell the state machine, hey, this is a configuration. The next 2 or 3 bytes are configuration bytes. Take that configuration, load them into the registers of the state machine, and basically have at it. So, I mean, this is kind of getting to the kind of stuff that we teach in some of our classes. I mean, this is an assignment that we would normally do from scratch and let everyone implement this and basically do it. But just to give you a feeling for it, using the correct programming language, i.e. Verilog, this is only, let's say, maybe 50 lines of code, something like that. So it's very little code that you actually need to implement in the FPGA, just because it's essentially a state machine with 2 counters. So would the NXP PN 547 be susceptible to this? So I'm not familiar with that one. I mean, this is really the issue here is that NXP uses this. I mean, which is typical for a company making embedded microcontrollers. They a lot of times. So let me just set that aside. A lot of times they'll use the exact same boot ROM across multiple devices. So they'll write it once and then use it in every single member of the family. And so that's the biggest issue that we're seeing right here. So basically every NXP LPC, doesn't matter whether it's automotive, whether it's used in planes, what have you, they're all going to be susceptible to this. I mean, I've seen there's a substantial amount of like USB devices that also use them. I mean, they're not as popular as the STM32s, but they are popular nonetheless. So those kinds of devices have them as well. Yeah. I mean, so, but if you're looking at larger devices, I mean, there's, it's an interesting question. So if you're talking about something like an SoC, ironically, the more complex the system is, the easier it is to pull off an attack like this. So if you look, I mean, some people think that even the iPhone boot ROM glitches were initially found using glitching similar to what we're doing here. Additionally, there's been work, for example, against the STM32. So the STM32 is actually an interesting example because the STM32 uses an internal power supply, which is, in that sense, it's fairly similar to what you would see on larger devices. So let's say an ARM SoC or something like that. So basically, you also have to deal with all the things related to having an external power supply and internal power supply. I mean, ultimately, that's the biggest issue that you'll have when you're glitching or trying to apply this attack to larger devices. So if you are actually looking to try this out against something like an SoC or something like that, I recommend you start with, the STM32 is probably the best example we've come across, just because the STM32, especially the F2, the F2, I can say just because Thomas and I did a talk at CCC about glitching the STM32 F2. That one's particularly easy once you know all the tricks, but it's also very close to what you would see in a larger device like an SoC. So let me check chat one more time, but if not, I think that pretty much covers it. So at least a second ago was the last question. So yeah, so that's pretty much it. So so if you guys are interested in this stuff, whether that's doing stuff on the FPGA, so doing stuff on the FPGA, or so if you guys are interested in this stuff, whether that's doing it on the FPGA or it's doing the kind of stuff that Thomas was showing in Ghidra, then make sure to check us out. So and you guys can feel free to use Hack in the Box as a discount code to register for some of our classes. We'll be happy to see you there and to show some of this stuff when you're doing one of our classes, and specifically, whether that was the stuff that Thomas was showing today with SVD loader or this kind of stuff. That's the kind of material we cover in our trainings. So thank you for listening in on this one.
Cool. Thank you very much.